Hello everyone and welcome to this Copernicus Marine Service practical session about waves in the Arctic Ocean. My name is Sylvain. I'm a scientific engineer at NOVELTIS and I will be your trainer for this session. Today you will use a Jupyter notebook to learn how to handle CMEMS product and more precisely how to visualize waves during a storm event. This training is based on a Jupyter notebook, and before starting I have two things I would like to remind you. The first one is that some cells in this notebook are composed of code in Python which you need to execute, running the cell. To run the cell, you can either click here, which run the selected cells and advance, or use the keyboard shortcut Shift plus Enter. The second thing is, if for any reason your kernel is not working anymore, it's not a problem. You can restart it using this button in order to restart the kernel, and then you can select all the cells you have already gone through to rerun them again using run all above selected cells. Since the polar ice surface decreases from year to year, the Arctic Ocean is very concerned by maritime transport with the opening of new route options. The sea conditions are also changing with the extension of the sea ice-free surface waters combined with strong winds, favoring the generation of waves. In this context, the objective of this exercise is to use the Copernicus Marine Service wave products to visualize waves during a storm event and during the whole year 2019 at three particular points of a potential future route in the Arctic Ocean. To be more precise, today you will learn how to handle and explore a NetCDF file, how to map the waves, how to create a GIF animation, how to plot time series, and how to plot wave. First, let's have a look on the data. This exercise is based on the Arctic Ocean Wave Analysis and Forecast product. The system uses a WAM model at 3 km resolution first, with surface winds and boundary wave spectra from the ECMWF, together with current and ice from the RC-MFC analysis. ECMWF stands for European Center for Medium Range Weather Forecast, and the RC-MFC analysis is the sea ice concentration and thickness. The WAM models runs twice daily, providing one hourly 10-day forecast and one hourly 5-day forecast. From the output variables, the most commonly used are significant wave height, peak period, and mean direction. The image below provides you a summary of this product. You get the geographical coverage, which is the Arctic Ocean, the level of the project, L4, all the variables you can find in the product, including sea surface wave significant height, its resolution, 3 km as stated before, temporal coverage, so you can find product from December 2017, and if you would like to get more info on the product, you can find more information on the dedicated product page on Copernicus Marine CMEMS web portal here. If you have more information about the product itself, the product user manual will be helpful, and if you are concerned about the quality of the product, the quality information document is here for that. Eventually, the products used in this notebook have already been downloaded for you, and they are stored in the data folder. You can access this folder right here and data. If you wish to download the data by yourself, you need to have CMEMS user credential. You can get them following this link. In order to download the product, here are the parameters that were used to download each dataset, giving the dimension and the frequency of the data. If you ever need guidance about the different services for downloading CMEMS project, before manipulating the data, we need to set up our Python environment and importing the necessary libraries. Those tools are available in the Jupyter Notebook ecosystem, but unlike MATLAB, the libraries need to be imported before they can be used. During this training, we will use several libraries, and there are summed up here. The OS module is the operating system interface and allows you to manage paths and create directories, for instance. NumPy allows carrying out scientific computing with Python and managing ND arrays. Xarray handles NetCDF files in an intuitive and interactive way. Matplotlib is a Python numerical plotting library. Basemap Toolkit is a library for plotting 2D data on maps. Datetime is a module which is useful to easily manipulate dates. And eventually, Pandas is a fast and powerful data analysis and manipulation tool. You will need to import those libraries to use them, but you can also import only portions of those modules. So in this cell, we import the OS module, NumPy Xarray, but we create an alias for NumPy and Xarray. So after, we just have to type np to call the NumPy module and xr for Xarray. Matplotlib is not useful completely. There, we just need the pyplot part. So we just import the pyplot part of Matplotlib as plt. Same for basemap. And we'll create an alias for pandas. A last module is imported, which is warnings, which is used to filter the different warnings you could get while running cells. To run this cell, I have to select it, and then either press run the selected cell, or use the keyboard shortcut Shift plus Enter. You could see that there was a little star showing that the cell was running, and now there was one here, meaning that this is the first cell that I have run in this kernel. So now everything is ready to use those libraries. If you would like to install the needed Python module for local installation, for instance, you could download this module by yourself. The libraries have been installed on the CMEMS Jupyter Hub ahead of this training session, hence you don't need to install anything. If you wish to replace this notebook later on your own infrastructure, you may need to check your Python version and install the Python libraries used in this notebook. So, if you want to check your Python library, because for this notebook you need to have a Python version of 3.7, you can use the Linux command Python version. In order to run a Linux command in a notebook, you just have to use an exclamation mark before. So I select it and run it, and I am on 3.7.3 version of Python. If needed, you can install the right Python version in this way using conda install python command. If you are using the standard Anaconda 3 installation, you can install the needed modules executing the following command in the new cell: conda install and all the modules that are required. Then you will need to restart the kernel, as we have seen. Now that the environment is set up, we can explore the NetCDF file content. First, we are going to work with the hourly dataset of the analysis and forecast wave product over the Arctic Ocean. In particular, we will use the dataset WAM over the Arctic 1 hour and 3 km with the dataset with this file name, which is already downloaded in your data folder. In order to open it, we have to tell the Jupyter notebook where it is. So we define two variables, which are the root path and the complete name of the file. The root path is only the data folder, and then the full name is the root path and the name of our file. Just running the cell, and the variables are defined. Now we can open this data. The Open Dataset of the X-array module allows to interactively browse the content of the file. Just running this, and we have access to a lot of information about these datasets. First we have the dimensions, telling us that this dataset is comprised of more than 1000 latitude and longitude and over 96 timestamp. There are different coordinates that are stored, data variables, and attributes, which gives you all kind of information about this product, from the title, the institution which created it, the date, all kind of things that you can find traditionally in a header of a file. You can access the attribute of a variable just clicking here, Show Hide Attribute. So this tells you that this variable is spectral significant wave height, HM0 in meters, and with a projection stir. You can also have access to the data representation here, and you see the number of values and the type they are stored in. So there are float values coded with 32 bits. Right now we have just opened interactively the dataset, but we need to store it into an X-array in order to manipulate it and use it after. So we just open the dataset and store it in an array and display the information, the header of this dataset. And you can find the same kind of information we had before. A NetCDF file, which is a base file of this dataset, is a common way of storing scientific data. It contains the dimensions of the data, here the time, latitude and longitude, several variables depending on one or more of these dimensions. You can see that those two variables depend on the time, latitude and longitude, and general information about the product. There are the global attributes that we have already seen, the institution, the title, the history of this product. You could, for instance, want to store one attribute of this variable, and you can access this easily using the attrs and then the name of the variable you want to find. So here the institution is the Norwegian Meteorological Institute, and we can just print it. You can print the different variables of NetCDF files with the function data vars, which are the three variables we have already seen right here. You can see that those variables depend on several coordinates. If you want to learn more and get more information about these coordinates, you can use the dataset point coords, which will print the coordinate of the NetCDF file. Those are the coordinates we have already seen before. If you want more information about the product dimension, you can either look at it right here or use the dims function. If you want to store the values of a variable in an array, you just have to type the name you want to give to your array, my array, equal to the values you want to store. For instance, if you want to store the time values of the NetCDF file in an array which is called var_time, this is the cell to execute. This cell just stores the values but doesn't display it. if you want to see what you have stored, just use the print function. You can see here that we have different dates, and there is an evolution of 1 hour between each between each date, and it starts on the 29th of November and it finishes on the 2nd of December. You have seen here how to see the information about a NetCDF file with Python function using X-array and accessing the different values. You could directly use the ncdump command, which is a Linux command, to see those information about the NetCDF file. Because it's not Python but Linux command, you need an exclamation mark before at the beginning of the command line in order for it to work. As for the Python version, we use the same exclamation mark before. We use the H option in order only to have the header of the file, and then you give the name of your file, and it will display the same information we have seen before. It's not as readable as it was with the Python import, but you have all the same information. It displays the same kind of information, but it's worth noted that it only shows time in seconds since a certain date, and not as a real-time format. Here you can see time units, seconds since the 1st of January 1970. Whereas when you use xr.open_dataset, it interprets the time coordinates as a useful date in year, month, date. Now that you know how to handle a NetCDF file, we can start our first exercise, which deals with the wave condition during a storm in December 2019. We would like to visualize the content of the product onto a map. And the variable of interest in this studied dataset are geographical variable. So in this exercise, we will plot maps during a storm event in December 2019. We will display maps every 6 hours, and then we will create a GIF animation to see the evolution along the time. The first step is to select the NetCDF file and the variable name. In this exercise, we will have a closer look at the significant wave height variables. The wave model products contains 4 types of significant wave height information, which are here the spectral significant wave height, spectral significant wind wave height, the spectral significant primary swell wave height, and the spectral significant secondary swell wave height. Now we will only consider the spectral significant wave height, the VHM0, which represents the global significant wave height. However, it can be interesting to look at the other variables to better understand which processes are at stake during the considered period of time. You could do that after this exercise. However, in order to limit the size of the file, only the first variable, the VHM0 data, was downloaded for this exercise. Downloading all the data could be a good training for you in order to check if you know how to do it properly. So we know which variable we need, but we need to define its name of the variable of interest in the file and its short name to put in the map title. So, as before, we defined the path of the file to open in the data folder. We defined the full name of the file, and then we define the name of the variables of interest for the exercise. We then open the NetCDF file with X-array module and open dataset function and store the variables of interest in individual arrays. So we get the variable var name VHM0, which is VHM0, and associate the associated coordinate and attribute and store them in this variable. And we do the same for the variable VMDR, and we print the resulting X-array dataset. Then we define short name for the variables. So it will be the spectral significant wave height here, SWH. Eventually, we store the coordinates in two separated variables. So we have imported in fin the dataset, and we want the time variable, so fin point time, and we want to store its values in a variable called time. So fin point time point values gives you all the values of time. It's the same for the longitude, latitude, and L lat. And we're going to print the time variable. The final step is to create an output directory to save the plot. It will be called out, and you can access it afterward right here. Let's see what it creates. So we have opened the dataset, so we have first printed the name here, print f name, which is root path plus name. Then we have printed the X-array dataset as before with the coordinate and attributes, and then we've printed the time variable, which we have already printed before, and then the plot folder. In order to spare some memory, we are going to close the dataset because we already saved all the variables. We are going to plot the variable of interest from the hourly dataset every 6 hours on one figure with one subplot per date. It means that there will be one image per date. We are going to use several functions. The first one is the subplot function from the pyplot module. Pyplot module was a sub-module from matplotlib module, and we imported it as plt. So we call plt.subplots. M and n are the dimensions of the array of figure we want to create. So this will create a global figure composed of m line and n columns. We can define the dimension of the figure with the fixed size function, defining the width and height in inches. When we create subplot, it is called an ax, and we can define the ax properties independently from the others. The base map function creates a map background and allows to define all the properties of the map: projections, plotting windows, coastlines, filling continents, for instance. The p-color mesh creates a pseudo-color plot with a rectangular grid. Eventually, the asType function allows to change the format of the object data into date type, for instance. You can define the type of the object you want to convert. We want to plot the variable every 6 hours, and as you've seen before, there are quite a lot of dates. So we could do it manually, but in order to have an easier process, we are going to use a loop on the time variable to automate the subplot generation. So first, we're going to plot the data. So on one figure, one subplot per date. We define first the minimal and maximal values for the significant wave height, and we create a subplots of 8 lines and 2 columns with a certain figure size. Then we create a loop on the dates to plot the data. So, as you may remember, the time array gets one value for each hour, but we just want to take one date every 6 hours, so we need a 6 of them. And we are creating a loop over the length of the time array divided by 6, because we just need 1 out of 6 of it, and the int function returns an integer object from any number or string, because this number might be a float number, but this loop needs an integer number. So we create a base map for each date, a base map instance with a stereographic projection, which is defined right here. And lat 0 and long 0 are the center of the desired plot domain. Then we add to the map coastlines, country boundaries, and filling the continents with the appropriate functions. We can also draw parallels and meridians. We can see here that the meridians are plotted between 30 and 360 degrees with a spacing of 60 degrees, and the parallels are plotted between 60 and 90 degrees with a spacing of 5 degrees each. We then plot our variable using the pcolormesh function. We take only one value every 6 value, because ti is for our loop and we just want every 6 hours, and we adjust the scale to the min-max value we have defined before. We add a color scale on the right of the figure in order to have the scale we are using, adding a title with the date info used in the title, and then after the loop is over we show our figure. The file is saved under the defined output directory with this name, and we print the name that is used. So I just run it, and it's going to take quite some time. It took several minutes to compute, but here are the results. So we have images on 8 lines and 2 columns as it was specified before. And in the as time elapsed, every 6 hours as asked, over the region that we specified. So we can see that we have medium significant wave height in the Norwegian Sea, and as time passes we have an increased significant wave height on the northeast of this sea, which slightly extend to the Norwegian and the Greenland Sea. And we can see that at 6 p.m. this is the end of this event. Finally, you can see that the file was saved in the out directory. These plots only show the significant wave height at different time. We can imagine that there is something going from the east to the southwest giving those images. But in order to be more precise on our analysis, we can map the significant wave height condition with the wave direction. So we want to plot the direction of the waves as vectors on the map, and we need to decompose the wave direction variable provided in degrees into the eastward and northward component of the direction, u and v. So we already retrieved the wave direction variable, and which is var_dir, but we first need to convert it into radian, which is why we multiply it by pi and divide it by 180 degrees, and then we get the eastward component taking the sinus of this value, and then the northward component v taking the cosine of the value. On the images we generated before, we are going to superimpose the wave direction, and for that we are going to use a quiver function. As before, we defined min-max value for the significant wave height. We reduce the number of points where to plot the wave direction to 1 out of 50, because imagine if you would plot an arrow of the wave direction for each point of this image, it would not be readable at all. So we choose to plot 1 every 50 pixels. Then we create our figure with subplots, same, so 8 lines, 2 columns, and we create a loop on the date, and we take, once again, 1 out of 6 data. The base map is plot, we draw the coastline, draw countries, fill in continents, drawing meridians with the same spacing and parallels as well, and we take the projection from latitude, longitude to XY coordinates. Then once again we plot our data, which is a significant wave height, with P color mesh, and then, this is important, we add the wave direction vector with the quiver function. So on the X, Y, U and V, U and V being the eastward and northward wind component, we only take 1 point out of point step. So here we take 1 point out of 40. And we do it 1 time every 6 hours. The following is the same as before. We add color scale, title, and we save our file. Just execute it and wait for it to run. Here we have the result. So we have the same picture as before with a significant wave height, but with an added wave direction. So we can see that at the beginning of the day in the Norwegian Sea, the wind was mostly going southwest, and as we have a more intense phenomenon happening here with important wave height, the wind and wave direction is following this propagation of this important significant wave height, going firstly west, then southwest, and then directly south in the Norwegian Sea. And as this phenomenon is disappearing, we find again the same. We have created a figure which shows the significant wave height and the wave direction during the storm event, but it required a lot of space on our notebook to display those images. Maybe using a GIF animation it would be easier to represent this storm event and to catch the specificity of this event. So to do this, we are going to use the same file and variables as above, so there is no need to redefine them. However, to have a smooth animation, we are going to plot the maps on an hourly basis. On the previous image, we were 1 image per 6 hours, but for our GIF animation, we can afford to do it every hour. So the first step is to define our output directory, which will be this one, and the path for it. Then we are going to generate a map just like before. Small difference will be that it will be every hour and not every 6 months, so it will be a bit longer. It will take quite some time to compute. In my case, I've already run it to save some time, and here's the result. It created all those images in the out GIF folder. It is quite time consuming, because if it took you some time to generate the previous figure, this one will be 6 times longer, so be patient. In order to be sure that it has finished to run, just check here. If there is a little star, it's still running. Don't stop it. But if you have a number like me, it's finished and you can proceed to the next section. To create the GIF animation, we are going to import 2 libraries. ImageIO is a library that provides an easy interface to read and write a wide range of image data, including GIF. And Pathlibs allows you to manipulate more easily the different paths. So we just need to import those libraries. Then we are going to look for our images in the out GIF directory, and we stock all the images name in the variable image. So we create a list with looking into this directory all the images on PNG which start with this name and have a different date and value afterward. And so we have a list which is sorted in ascending order. Then we store all the images in the variable image list, which is a list of the images. So we add to the list the name which is called by the file name stored in this list, which store, as a reminder, all the images which are available in the out GIF directory. Let's just run it. The next step is to create a GIF. So we are going to create it and call it animated storm. The duration is the time between two images in seconds and with 10 loops, and we're going to save it in this directory. It takes quite some time to compute it and to create it and then to save it. It's done. And we are going to use the IPython display function, some module, to display this GIF. Let's see what it looks like. The GIF is created, and you can see that the title is changing with the time going on, and we have the significant wave height hour by hour displaying our storm event in the Norwegian Sea. So you can see that there is a quite strong increase of the significant wave height at the beginning in the northeast of our plot, which propagate to the southwest. In this exercise, we have displayed maps of significant wave height and direction during a storm event, where we could see the storm coming from the northeast. On the maps of the last time frame of the dataset, we can also notice a second storm coming from southwest. We can see here at the end of the storm event. Between Svalbard and the eastern coast of Greenland, we note that the waves are stopped by the presence of sea ice. Here, you can see that there is no propagation of the waves. The sea ice cushions the impact of the waves, and we can note that the sea ice limit moves a little over the time, but substantially remains at the same position. You can see that it's moving a bit, but globally not so much. Finally, just a tip. This GIF is quite resource consuming. It's quite big, and if you want your notebook to run smoothly for the next exercise, we advise you to clear the output of the previous cell. To do so, you just have to click on this cell, then go to Edit, and then Clear Output. GIF has disappeared, but it's way better for your notebook if you run on a smoother way. You can still have access to the video you created because it was saved in the out GIF folder, and it's here, animatedstorm.gif. In the first exercise, we studied one storm event at a precise time and location. In this second exercise, we are going to analyze the wave evolution during the year 2019 in 3 different points. Since the polar ice surface decreases from year to year, the Arctic Ocean is very concerned by maritime transport with the opening of new route option. We are going to plot the wave condition with rows and time series at 3 points, which are defined by those longitude and latitude. In order to plot them, we define an array with the coordinate of the points, creating a figure with a base map, filling continents, drawing parallels, meridians, and we plot our points. So here are the position on the map of the 3 points we are going to study. The goal of this exercise is to plot a wave roses. In order to do so, we need to import a corresponding module which is called WinRows. Then we need to select the NetCDF file and the variable names. Here we will have a closer look at significant wave height, which is with the variable VHM0, the wave direction with the variable VMDR, and the sea ice thickness SIT variable. All those variables and datasets were downloaded for the three considered points. So we are going to open the dataset, extract the variables and coordinates of interest, and close them afterward, defining the root path to the data folder, the three names of the datasets, the three name of the variable of interest, opening the dataset, extracting the variable that we are looking for with their coordinates and attributes. We define then a short name for the variable, and we take latitude and longitude and time variables. And eventually, we close the dataset in order to spare some memory. The configuration to plot our wave rows need an output directory, so we just create it. Then we define the parameter for our WinRows function. So the parameter for the significant wave height, it will be divided in a different section, and we will start at 0.5 meter up to 4 with spacing of 1, meaning on our WinRows we will have 4 different sections for the significant wave height, between 0.5 and 1.5, between 1.5 and 2.5 meters, between 2.5 and 3.5, and then above 3.5. Then we need to determine the range for this, so we create an array starting from this minimum to this maximum, so it's the limits that I've just explained, and we create a number of directions for our wave rows. Here we are looking at 20 different directions, so as the wave rows will be 360 degrees, each direction will be 18 degrees each. Now that this is defined, we can extract our wave height and wave direction. So for the wave direction, we just take it as integer number, and for the wave height, we round them to value to number after the comma. In order to be able to use those arrays, we have to transpose them. It's just transposing the data for it to be in the correct shape to be used by the WinRows function. Plotting the WinRows is quite straightforward. We create a figure with a WinRows module, and then we define our bars in it. So giving the direction, the wave height, the different bins for the wave heights that we've defined, so there are 4 of them, and the number of sectors, there are 20 of them. We add to this plot a legend, one title, and we save the file. So this is our wave rows. So this is a direction where the waves are going. You could ask me, but where? This is latitude and longitude. Why is that at this point precisely? Latitude 70.75, longitude 18.59. Because when we defined our point, we defined the 3 points here, but there is the same variable name right there. So we first define fname, and then we rewrite it, and then rewrite it again. So it is a point 3 we are looking at. So if you look at point 3 coordinates, it's indeed 18.59 in longitude, and it's what was displayed before. If you want to see what happened for point 2, you just have to comment this line. You can do a comment with this symbol, If you want to see what happened on point 1, just comment the 2 other lines and check on the title of the figure if you have on the right point. So, what can we observe on these wave rows? First thing is that most of the wind are going eastward, northeastward, and southwestward. But the higher waves are with winds going northeast-eastward, whereas you have medium wave height in this direction, but you have really a low number of events during the year in the northwest direction. In the first exercise, we studied one storm event at a precise time and location. In this second exercise, we are going to analyze the wave evolution during the year 2019 in 3 different points. Since the polar ice surface decreases from year to year, the Arctic Ocean is very concerned by maritime transport with the opening of new route options. We are going to plot the wave condition with rows and time series at 3 points, which are defined by those longitude and latitude. In order to plot them, we define an array with the coordinate of the points, creating a figure with a base map, filling continents, drawing parallels, meridians, and we plot our points. So here are the position on the map of the 3 points we are going to study. The goal of this exercise is to plot a wave roses. In order to do so, we need to import a corresponding module which is called WindRose. Then we need to select the NetCDF file and the variable names. Here we will have a closer look at significant wave height, which is with the variable VHM0, the wave direction with the variable VMDR, and the sea ice thickness SIT variable. All those variables and datasets were downloaded for the 3 considered points. So we are going to open the dataset, extract the variables and coordinates of interest, and close them afterward, defining the root path to the data folder, the 3 names of the datasets, the 3 name of the variable of interests, opening the dataset, extracting the variable that we are looking for with their coordinates and attributes. We define then a short name for the variable, and we take latitude and longitude and time variables. And eventually, we close the dataset in order to spare some memory. The configuration to plot our wave rows need an output directory, so we just create it. Then we define the parameter for our WindRose function. So the parameter for the significant wave height, it will be divided in different sections, and we will start at 0.5 meter up to 4 with spacing of 1, meaning on our WindRose we will have 4 different sections for the significant wave height, between 0.5 and 1.5, between 1.5 and 2.5 meters, between 2.5 and 3.5, and then above 3.5. Then we need to determine the range for this, so we create an array starting from this minimum to this maximum, so it's the limits that I've just explained, and we create a number of directions for our wave rows. Here we are looking at 20 different directions, so as the wave rows will be 360 degrees, each direction will be 18 degrees each. Now that this is defined, we can extract our wave height and wave direction. So for the wave direction, we just take it as integer number, and for the wave height, we round them to value 2 put a number after the comma. In order to be able to use those arrays, we have to transpose them. It's just transposing the data for it to be in the correct shape to be used by the windrows function. Plotting the windrows is quite straightforward. We create a figure with a windrows module, and then we defined our bars in it. So giving the direction, the wave height, the different bins for the wave heights that we've defined, so there are 4 of them, and the number of sectors, there are 20 of them. We add to this plot a legend, one title, and we save the file. So this is our wave rows. So this is a direction where the waves are going. You could ask me, but where? This is latitude and longitude. Why is that at this point precisely? Latitude 70.75, longitude 18.59. Because when we defined our point, we defined 3 points here, but there is the same variable name right there. So we first define fname, and then we rewrite it, and then rewrite it again. So it is a point 3 we are looking at. So if you look at point 3 coordinates, it's indeed 18.59 in longitude, and it's what was displayed before. If you want to see what happened for point 2, you just have to comment this line. You can do a comment with this symbol. If you want to see what happened on point 1, just comment the 2 other lines. And check on the title of the figure if you have on the right point. So, what can we observe on these wave rows? First thing is that most of the wind are going eastward, northeastward, and southwestward. But the higher waves are with winds going northeast-eastward, whereas you have medium wave height in this direction, but you have really a low number of events during the year in the northwest direction. As a comparison, I've plotted here the wave rows for the second point, and we can clearly see here that the wave height is lower and that there is one major direction for this, which is from northeast-east to southwest-west. Now let's have a look at the data. We can have a look at the frequency values used by windrows and generated by the plot function axinfo. So we are going to look at the shape of this table, which is 420, 4 being the number of bins for wave height and 20 the number of bins for the direction. We create a Panda data frame from this information and see what it looks like. So we indeed have a table with 20 columns corresponding to the direction and 4 lines which correspond to the different wave height. So we can see that there is 0 frequency here for the 4th wave height bin, and we can see of this windrows that there is no really high wave height above 3.5, and it is, I think, on this direction of the on the 14th that there is a highest number here. It corresponds to this peak here, right here. We can also print a table with all the data of significant wave height and direction used to generate the plot. So from the Panda data frame, we select display all the time value, and we display for all those time value the significant wave height and the direction. And for each time value, we have this information. It's make quite a lot of data, nearly 9,000. We can save this data in a file in CSV format and to store it for later analysis. It is stored under the name Now we are going to plot a time series in order to analyze the evolution of the significant wave height and the sea ice thickness during the whole year 2019. First, we create the output directory to save the plots. Just create a new directory if it's not existing. Then we display a figure with the sea ice thickness variable and the significant wave height variable. This will be a dual graph with both variables displayed along the time. So we first define the first color, which will be red, and second one blue. We take our variable, significant wave height, and sea ice thickness, and we will plot them along time. We first plot the first variable, setting the y label, which is significant wave height, along the time, and then plot the second one. We give a title to our graph, and then we are going to save the file and print it. Let's see what it looks like. So we have spectral significant wave height and sea ice thickness along the time for the 2019 year. So in red it's the significant wave height, in blue sea ice thickness. It is quite interesting because we can clearly see the dependency between the wave height and sea ice. When there is sea ice, so when this value in blue is above 0, you can see that in red there is nearly no waves or very low waves, and when there is no sea ice, the wave increases. This is the end of this training about waves in the Arctic Ocean. I hope you learned things, and notably how to handle CMEMS wave products, how to open them, how to plot them, and how to make GIFs, for instance. Thank you for your attention. I hope you enjoy this training provided by Copernicus Marine Service for free, thanks to the European Commission. You can now try to download new data and variables and to access and visualize them. You can try to make new maps and plots. You can try other Copernicus Marine Arctic products which are